Example of a projectile problem. This time we're going to look at an angle when it's launched at an angle, and delta y is equal to 0. In other words, it lands at the same exact height that it started at. Okay, so we're going to look at number 35 on page 72, and it says a projectile is fired with an initial speed of 75.2 meters per second at an angle of 34.5 degrees above the horizontal on a long, flat firing range. Determine A, the maximum height reached by the projectile, B, the total time in the air, C, the total horizontal distance, that is the range, and D, the velocity of the projectile 1.5 seconds after firing. Okay, so first thing I want to do is sketch this out. Something's being launched at 75.2 meters per second at a 34.5 degree angle. It's launched out and it lands somewhere over here. We're trying to find this distance, we call delta x. We're trying to find the maximum height, we'll call that y max. We're trying to find the time in the air, and we're trying to find the velocity after 1.5 seconds. Okay, so again, it's a projectile problem. We want to break it up into horizontal and vertical components, just like we did on the other one. Okay, the delta x, we don't know how far away it's going to land, so it's unknown. VO, we don't know yet, but we can find. AX is still 0 because it's always 0. Delta y is 0. We know that because it lands at the same exact height it started at. VO in the y direction is unknown this time. And AY is negative 9.8 meters per second squared. Now, be careful. Make sure you don't put in this velocity of 75.2 meters per second in for the horizontal or for the vertical. That would be incorrect because it's not launched horizontally or vertically. It's at an angle. So our first job here is going to take that velocity of 75.2 meters per second and figure out how much of it is horizontal and vertical. So we form a right triangle out of it. Here's the horizontal leg. We'll call that Vx. And here's the vertical leg. We'll call that Vy. We make a right triangle. Vx is going to be 75.2 cosine of the angle, which was 34.5 degrees. And we'll plug that in the calculator. And Vy will be 75.2 sine of 34.5 degrees. So we're going to hit those in. So 75.2 cosine 34.5 gives me 61.97. So we're going to call that 62. And the other one is 75.2 sine 34.5. And we get 42.6 meters per second. Okay, so now we have more information. Again, we're going to look at our two accounts of the information, say which one has all the information. The vertical does. So we're going to use the delta y equation. Delta y equals VOT plus 1/2 AT squared. And we're going to solve it for the time. Okay? We know that delta y is 0. VO in the y direction is 42.6 meters per second times t plus 1/2 negative 9.8 meters per second squared times t squared. So I'm going to clean this up a little, and it's going to look like this. 0 equals 42.6 t minus 4.9 t squared, because a half times negative 9.8 is negative 4.9. Okay, so this is, I hope you realize, this is a quadratic equation. It has two solutions. One of them is pretty obvious, because what you're trying to figure out is, at what time is the height of this projectile 0? Well, one of them is right here. That's at the very beginning, when t equals 0. The other time is at the end, which we don't know, and we're trying to find. So using this equation will give us both of those answers, as you'll see. So what I'm going to do is factor out a t. So I have t times 42.6 minus 4.9t. And the reason I do that is now because if you have 0 equals something times something else, one of the somethings must be 0. So either t equals 0, which is a solution we already realized, it's trivial, or 42.6 minus 4.9t equals 0, and we'll solve that. So we subtract 42.6 from both sides and divide by negative 4.9, and that'll give us the time. We get 8.69 seconds. So that's the time it's in the air, the full time. Okay, now to find the maximum height. If it's on a level range, it's going to reach its maximum height at half of the full time. So we're going to use this equation again, but instead of plugging in 8.69 seconds for t, we'll plug in half of that, and that'll tell us at what height it will be at that time. So y max equals 42.6 times half of that time, 8.69 divided by 2 is 4.35 plus 1 half negative 9.8 times 4.35 squared. So we have to punch that all in the calculator. 42.6 times 4.35 minus 4.9 times 4.35 squared. We get 1760. We're going to check that just to be safe. So 42.6 times 4.35. Okay. Minus 4.9 times 4.35 squared. Okay, I'm getting a totally different answer. It didn't seem right. It's 92.6 meters, which seems much more reasonable. Okay, to find the range, that's delta x, we do the VOT plus 1 half AT squared. The A is 0 in the x direction, so delta x just ends up being VO in the x direction, which is 62 meters per second, times 8.69 seconds, and delta x comes out to be 62 times 8.69, 538.8. Okay, so I have that. Now the last part is, how fast is it going after a second and a half? Well, horizontally, I know how fast it's going, 62, because it doesn't change. But vertically, it's not going to be 42.6. It's going to be something less than that, because it's going to slow down. So what I need to do is find out how fast it's going in the y direction after a second and a half. I'm going to use VF equals VO plus AT. Okay, VF equals 42.6 plus negative 9.8 times 1.5 seconds, because that's the time they gave us. So 42.6 minus 9.8 times 1.5 gives me 27.9 meters per second in the y direction. So I have 62.2 in the x direction and 27.9 in the y direction. So I have to find the hypotenuse. I'll use Pythagorean theorem. 62.2 squared plus 27.9 squared. Take the square root. 68.1 meters per second. And it's still moving in an upward direction. We can get the angle by doing inverse tangent of 27.9 divided by 62.2, which is opposite over adjacent. We take the inverse tangent, and we get 24 degrees in the upward direction. I apologize that this one's kind of cramped here, but that's how we get the result.